Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in Applied Electronics. We are going through this paper on physics of materials, which deals with the important chapter on semiconductors. In this chapter, we are going through the lecture 4, and the contents of this lecture are as follows: intrinsic semiconductors, electrons and holes, intrinsic conductivity, density of states, and Fermi-Dirac distribution function. The electrical conductivity in intrinsic semiconductors ought to be calculated. Why should you calculate the conductivity, or why should you calculate the current? When you want to use a semiconductor as a half wave rectifier, you need the IV characteristics. You need a graph connecting the current and voltage, right? When you apply a voltage, you need the IV characteristics ought to be determined. Whether you use it as a half wave rectifier or a full wave rectifier or amplification, in all these cases the current voltage relations ought to be obtained, or in other words the current is to be calculated. So, let us now see in a intrinsic semiconductor how the current can be calculated, or the electrical conductivity can be calculated. Now, in the case of a metal, how do you write the electrical conductivity? You write sigma. The electrical conductivity is written as N into E into mu. What is N? N is the number of electrons per unit volume in a metal, E is the charge of the electron, and mu is the so called mobility. What is mobility? It is the ratio between the drift velocity to that of the applied electric field, right. We will do a few problems later, but you can now remember mu, the mobility will be the drift velocity per unit electric field. It is the ability or the freedom given to the particle to be mobile, to freely move when you apply an electric field, that is the mobility. Okay. And that is the definition I gave for a metal. But in a semiconductor, all of you know by now, you got a valence band and a conduction band, and we talk of electrons in the conduction band and holes in the valence band. And so, the conductivity is partly due to electrons in the conduction band, and also the conductivity comes from the holes to which we assign a positive charge. The holes in the valence band also will take part in electrical conduction. So, the conductivity will be a sum of the two terms. Sigma will be equal to N E into mu E. What is this term? This is the conductivity due to the electrons in the conduction band, whereas the second term is the conductivity due to holes. So, H refers to a hole and E refers to the electron. Electron has got a negative charge, hole is assumed to or supposed to have a positive charge, and so there will be the two contributions, one coming from the electrons, the other coming from the holes. The hole concentration and the number of holes per unit volume, the charge of the hole, it is taken as obviously as plus C. This will be taken as a negative sign in principle, and mu h is the hole mobility, whereas the electron mobility will be mu e, as explained in the next slide. That is, sigma is the conductivity in a intrinsic semiconductor, Ne and Nh are the electron and hole concentrations, mu e and mu h are the respective mobilities of the electrons and holes, and E is of course the charge of the electron. Now, what is the thing that we should arrive at? Now, we are trying to obtain the expression for the electrical conductivity. For that, what we will do is, let us see how we can calculate the first term. How much is the current due to electrons which are residing in the conduction band? How will you calculate the conductivity coming from the electrons in the conduction band? You got a conduction band, right? In the conduction band, how many energy levels are there is to be first known, right? How many energy levels are there in the conduction band, and to what extent the electron in a particular energy level will give rise to conductivity or will take part in, whether a given energy state is occupied or unoccupied also should be known. How many states are available and whether every state is occupied or unoccupied, to what extent is occupied, this also should be known. Therefore, how will you know how many states are there in a given band? That is given by what is called density of states, right? Density of states will give you how many states are available in a given band. Whether energy level is occupied or unoccupied is given by which distribution function? The Fermi-Dirac, because you are dealing with electrons, they are fermions, right? They are spin-off particles. They have to obey the Fermi-Dirac statistics. Now, therefore, whether energy level is occupied or unoccupied is given by the Fermi-Dirac distribution function. Therefore, you have to couple these two, the density of states and the Fermi-Dirac distribution function are to be coupled to calculate the current coming from the electrons in the conduction band. That is what you have to do essentially. Supposing you have got an electron here, you have got a plate which is positively charged, you got a plate negatively charged, you apply a potential, right? You have you got a battery here, this is a positive is connected here, negative is connected here, then the electron will move in this direction, okay, towards the positive plate, and the conventional current will be in this direction, opposite to when the electron is going, the conventional current is said to be flowing in the opposite direction. You got a hole here, the current it will be moving in this direction, electron is moving in this direction, means the opposite charge hole will move in this direction, okay, with a velocity V h. The current also will be in this direction, okay. So, I e the current due to electron and the I h the current due to electron, both of them will be in the same direction. This is a very important point. So, the current due to electron and the direction of the current due to electron and the direction of the current due to hole, both of them are in the same direction. This justifies, this makes us to sum up the two currents, right. I e plus I h will be equal to the total current. That is what we will be doing in the time to come. We will be summing up the contributions coming from the conductivity due to the electrons and the conductivity due to holes, or the currents, or will be summed up because they will be same direction, okay. The I e is in this direction, I h also will be in the same direction, okay. And so, electron and hole conductivities or mu e or and mu h or the respective currents I e and h, there the mobilities are given here, the currents are given here, the currents can be summed up, and important point we noted is both the currents are in the same direction. As I showed you just now, both the currents are in the same direction. that justifies us to summing up the two currents, right. Okay. That is important point. The number of electrons available in the conduction band depends upon two factors. The point to be noted down is, now the problem is how to calculate Ne, the number of electrons available for the conductivity in the conduction band. This depends upon the two factors, the number of electronic energy levels available in the conduction band, that is one thing, that is given by so called density of states. Whether the state is occupied or unoccupied is given by the Fermi-Dirac distribution function. What is Fermi-Dirac distribution function? It gives the fractional occupation probability for the electron to be found in a particular energy level. You take a particular energy level and you ask the question whether that energy level is occupied or unoccupied. When we discussed about the movement of electrons in metals, we drew a graph between f of E and the energy. We had a rectangle at 0 Kelvin. When a metal is kept at 0 Kelvin, we have what is called the Fermi energy and all. So, the probability will be 1 up to Fermi level. So, the extent to which the energy states are occupied is given by so called Fermi-Dirac distribution function. So, in essence, what I am trying to impress upon you is the fact the two factors, that is the density of states, should be coupled with the Fermi-Dirac distribution function in order to determine the number of electrons available in the conduction band to take part in electrical conductivity or in calculating the electrical conductivity. Now, this is something like this. A teacher goes to a classroom and he wants to find out how many students are there. How do you find the number of students? You have 20 benches, right. 10 benches on this side and 10 on this side, the 20 benches are there, right. So, you find the number of states or the number of benches available, right. The 20 benches are there. In the first bench, how many students are sitting? That is given by the Fermi-Dirac distribution function. The first bench, there are 2 students. The second bench also you have got 2 students. The third bench there will be 2 and the fourth bench there will be only 1. So, the fractional occupation, whether the benches are occupied or unoccupied is to be found out. So, in order to calculate or in order to determine how many students are there in a classroom, what you have to do is you have to count the number of benches and you have to see whether each and every bench is occupied. If so, to what extent is occupied, whether 2 boys are sitting or 2 girls are sitting or 1 boy is sitting. Okay. Likewise, this gives the number of benches available or number of states available, and this one gives whether the state is or bench is filled up. You see in a classroom a bench is filled up. Similarly, here the energy level whether it is filled up or unfilled. In the case of the classical case where when you are talking about bench and students, you cannot have 1.5 student, right, or 1.7 student, but here you can have fractional occupation. The occupancy will vary from 0 to 1. I cannot have 2 and so on. So, the Fermi-Dirac distribution function will vary from 0 to 1 and fractional occupancy is obvious, right. At a finite temperature, f of E will vary from any value, it will take from 0 to 1. It may be 0.35 or it may be 0.727 and so on. So, the extent to which the energy state is occupied is given by the Fermi-Dirac distribution function. The analogy which I gave is very clear. Find out the total number of benches or find out the total number of states available and whether every state is occupied or unoccupied. Both these things are to be coupled to find out how many electrons are there. It is similar to how many students are there. So, that is the thing that should be done. So, this is the density of states. This is the so called Fermi-Dirac distribution function. Let us have a break at this point and we will resume the rest of the things after the break. Welcome back after the break, and our aim of this lecture is in calculating the electrical conductivity in the case of semiconductor, as I told you, the conductivity comes partly from the electrons and partly from the holes, and we are now concerned about the first part. In the first part, we want to find out Ne, the number of electrons in the conduction band. To find the number of electrons in the conduction band, I gave you the analogy. In a classroom, how many benches are there, and whether the benches are occupied or unoccupied, both the things ought to be known. So, in continuation with the analogy, I want to, the similarity I am going to bring out now. The first one, how many benches are there, is similar to how many energy levels are there in the conduction band. This is the conduction band. You have got a valence band, there is an energy gap and the conduction band. How many energy levels are there? That is something like how many benches are there. The number of energy levels available in the conduction band is given by an expression of this kind, that of course, all of you know by now. Should be, we came across this when we discussed the free electron theory of metals. We arrived at an expression for the density of states. What is meant by density of states? The number of states available in a particular energy interval, or you say in 1 electron volt, how many energy levels are there, right? In a energy level, what is the unit of energy? It is electron volt. What is the energy of the electron in the hydrogen atom? It is 13.6 electron volt. So, electron volt is the unit of energy in atomic physics. Now, therefore, in a particular energy interval, namely 1 electron volt, how many energy levels are there? It is given by the so called the density of states expression that you find here, right. Now, having got the number of energy levels, you ask the second question, as we asked with regard to the number of students in the classroom. We asked the question whether a student is sitting in a bench, how many students are there in a bench. Similarly, here the corresponding thing will be, you have the Fermi-Dirac distribution function. It gives the occupation probability, whether energy level is occupied or unoccupied by the electron, right. We are talking about the electrons in the conduction band. So, in a particular energy level, whether you have the electron or not, if you have the electron, to what extent the electron is there, whether the probability, as I told you, will vary from 0 to 1. In the classical case, when I talked about the number of students, the number of students in a bench may be 2 or 3 or something, but here there will be a fraction occupation. The occupation probability will vary from 0 to 1. That is given by so called Fermi-Dirac distribution function. First, you have to find the number of energy levels, how many energy levels are there in the total conduction band, then whether in every energy state how many electrons are there. The occupation probability ought to be found. So, you have to couple these two. So, coupling means what? You have to multiply these two, and then you have a energy interval dE, then you have to integrate properly using the proper limits in the conduction band. The conduction band, the bottom to the conduction band top, as you will see in the slides to come. Okay. In an intrinsic semiconductor, the Fermi level will be lying in the middle of the forbidden gap approximately. Now, when we derive the entire expression, as I told you just now, the Fermi-Dirac distribution function will be given by an expression of this kind. You have got a plus 1 here, right. This plus 1 can be omitted. When can you omit? If the first term is going to dominate, right, over the second term, when will you omit this one? The 1 can be omitted if E minus EF is much greater than KT, right. It is e power infinity is infinity, right. Infinity plus 1 is infinity, right. 1 can be omitted, right. Infinity plus 1 is infinity. So, this 1 can be omitted if the first term is a dominant term. When will it dominate? E minus EF should be large compared to your KT. Justification to find that this E minus EF is much greater than KT is given by the following argument. The typical value of E minus EF for silicon will be 0.5 electron volt. The typical value for this one will be 0.5 electron volt, because the energy gap is 1 electron volt. The Fermi level, as I told you, lies Midway means what? Out of 1 electron volt, half of it will be 0.5. So, the typical value of E minus Ef for silicon will be 0.5 electron volt. This we will show at the end, right. Now, and the value of Kt, K multiplied by 300 will be simply 1 by 40 electron volt or 0.025 electron volt at room temperature. So, K multiplied by 300 will be 1 by 40 of electron volt or 0.025 electron volt. So, compared to 0.5, this 0.25 is very small. So, you have got in the numerator 0.5 and 0.25 in the denominator. So, this one will be dominating something like infinity, right. Because of this fact that the numerator is very large compared to the denominator, this will be a dominant term. The exponential value will be very large compared to the plus 1 that you have got in the Fermi-Dirac distribution function, and this justifies the omission of the unity, the one that you have got in the denominator, because this E minus Ef is large compared to Kt. So, this is something like e power infinity, this one can be omitted compared to the first term, the one has got a trivial value, it can be omitted. This is what I have done here, right. The one in the denominator can be omitted. The energy of the electron is expressed with respect to Eg. Eg is the bottom of the conduction band. This is 0 he is taken here in the energy axis, the valence band, the conduction band. You assume this has to be equal to 0, right. This is the energy gap, obviously this Eg is the energy gap. So, the energies here are expressed in terms with respect to Eg, right, with respect to Eg or in terms of Eg. That is the reason why I have got E minus Eg here, right, because energy levels of the electrons residing in the conduction band will be expressed with respect to Eg, because Eg is the bottom of the conduction band. This is what I show here, Eg is the bottom of the conduction band. Okay. The energies will be expressed with respect to Eg. Okay. This is the energy band model to calculate the electrical conductivity. The energy of the electron E is expressed with respect to Eg, the bottom of the conduction band as shown below, and the top of the conduction band is taken as infinity, because you do not know the top. The top of the energy level can be taken as infinity, because mathematically it is acceptable, right. You take the upper limit as infinity. Now, we will do the integration, right. The number of electrons in the conduction band is obtained by integrating the following expression between the above mentioned limits. What are the limits? One is the Eg, the upper limit is infinity. So, we have to, I told you that you multiply the density of states and the Fermi-Dirac distribution function, you couple these two, you have to know the number of benches and the number of boys, similarly number of energy levels and whether the level is occupied or unoccupied. What is the integration? It is nothing but summation, right. To find the number of electrons or to find the number of students, you have to find how many benches are there and in each bench how many students are there. Similarly, here the analogy is very close, the number of energy levels and to what extent each and every energy level is occupied by the electron. So, by knowing the density of states expression and the Fermi-Dirac distribution function, by integrating or summing over the energy interval, the whole of conduction band, the energy limits are Eg and infinity. Okay. This expression will give you the number of electrons in the conduction band. I think it should be clear, right. I have given a very good analogy. The justification for having the upper limit as infinity lies in the fact that the distribution function will tend to 0 when E tends to infinity. When E tends to infinity, this will become 0, right. Obviously, you can see from the expression of density of states, when E tends to infinity, this will become equal to 0. That is the reason why the having upper limit does not produce any harm, and so this is what you have here. Now, you have to put the expressions that you have for DE and FFE as will be shown here. Substitute the expression of density of states which I showed earlier, and then density of states, I mean the Fermi-Dirac distribution function, and so by substituting for density of states and Fermi-Dirac distribution function which are given above, we have the limit Eg to infinity, you got the integral here 1 by 2 pi square 2 m by h bar square to the power of 3 by 2 into E minus Eg to the power half into E e to the power of E f minus E by k t into d. That upon simplification, taking out the constant terms outside, accepting the variable E, the energy variable, right. You got the integral is done, integration is done with respect to energy. You have to pull out all the things. This integral can be evaluated using the gamma function, right. Changing the variable by substituting E minus E g by x, the integral will become x to the power of half into e power of minus x into dx. That turns out to be pi to the power of half by 2. So, the electron concentration becomes, when you do all these things, the electron concentration becomes Ne is equal to 2 into m into k t by 2 pi into h bar square to the power of 3 by 2 into e to the power of E f by k t into e to the power of minus E g by k t. Now, what is m? M is the mass of the electron, k is the Boltzmann constant, T is the temperature at which these things happen. It may be room temperature, or you can calculate the electron concentration at any given temperature. You know, the Fermi-Dirac distribution function strongly depends upon the temperature. You have f of E is equal to 1 by e to the power of E minus E f by k t plus 1. So, the temperature term comes there. So, it is a obviously temperature dependent thing will be there. So, your T is found here, T is found here also. The energy gap will depend upon the temperature. Now, you know, pi is a constant, h bar is the Planck's constant times by 2 pi. H bar is nothing but the, what is h bar? The unit of angular momentum. H bar is h by 2 pi. Okay. The important point is the electron concentration depends upon the energy gap. Okay. This is one of the important things, right. For a given material, E f is again a constant, again E g also will be a constant for a given material. Okay. Now, in the case of intrinsic semiconductors, Ne will be equal to NH, and what you can do is you can try to obtain an expression for NH also. What we have done is we have calculated, we have obtained the expression of Ne. A similar expression can be obtained for NH. For an intrinsic semiconductor, the number of electrons which have gone to the conduction band should be leaving the same number of holes in the valence band. So, Ne and NH should be equal to one another. In the lecture to come, I will show how to evaluate NH. By equating Ne and NH, one can obtain the expression for the Fermi energy E f. The Fermi energy E f can be shown to be equal to E g by 2 plus 3 by 4 times k t times log of mh by me, where mh and me are the effective masses of the hole and the electron. If these two are equal, mh and me are equal, this will become 0. The Fermi level will lie the middle of the energy gap. So, now let me pass on to the summary of the lecture. Point number 1, in semiconductors, electrons are excited from the valence band to the conduction band even at room temperature. Coupling the expressions for the density of states and the Fermi-Dirac distribution function, coupling these two, one can obtain the carrier concentration of electrons and holes. The current due to electrons and holes can be summed up. I showed you how the justification for summing up the two. Now, we have the following questions. What is meant by intrinsic conductivity? Justify in summing up of the currents due to electrons and holes. What is meant by the term density of states? And lastly, explain the Fermi-Dirac distribution function. With this, we come to the end of the lecture number 4. The rest of the things with regard to intrinsic conductivity, extrinsic conductivity and other things we will see in the lectures to come. Thank you.